Welcome back, class, to the next lecture in the Verilog by example series. We are today going to look at the Verilog modeling of a zero detector circuit. So the idea is to take the FSM of the zero detector circuit and write the Verilog for it. And once we write the Verilog, the natural sequence is then it is sent through the synthesis tool, and the synthesis tool is responsible to generate the gate level circuit or the transistor level circuit for this particular Verilog model. Of course, we are not looking at the synthesis part of it. We will only concentrate in this class to generate the Verilog or to write the Verilog equivalent of the finite state machine. And this finite state machine, as an example, we will take of the zero detector circuit. So the zero detector circuit we have already seen in the class. This was one of the first sequential circuits in the that we saw in the class for the sequential circuit module. We will start with this FSM, and if you looked at the FSM, what it describes is, or what it captures is, basically the behavior of a circuit that can. This FSM describes a system that detects a zero after a bunch of ones. So for example, you might have something like this. So this FSM describes a system or a circuit that gives a 1 after this 0 input and a 1 after this 0 input. At all other inputs, the output will be equal to zeros here. Right. And let's quickly run through how this FSM represents the working of such a system. If you see, and you already know this, right? So this is the input on the edge, and this is the output described on the edge. And if the output is written on the edge, then you know that this is the combinational output, or this is the output that is generated by the current state or the present state of circuit and in combination with the input. So this output is a function of the inputs and the present state. Right. This kind of a circuit which generates an output as a function of the input and the present state is called a Mealy circuit. And the other kind of a circuit that generates output based only on the present state, or which generates output as a function of only present state, is called a Moore circuit. So this is a Mealy circuit, and it generates an output as a function of the present state, which is possibly this 1 0 if it is a state, and this input 1, for example. So if its present state is 1 0, and if the input to this circuit is 1, then the output is 0, right? So that's the meaning of this notation. On every edge there are a pair of numbers. So the first of the numbers indicates the input, and the second number indicates the Mealy output immediately generated after that input is applied. And you also know the transition between the states. That transition is also represented by this arrow from the present state to the next state based on this input that is there on the arrow. So let me erase a little bit of this just to be able to explain how this FSM describes the zero detector circuit. If you observe the inputs, so what we need is, what the desired event is this: after a sequence of ones, if there is a zero transition, then the output has to be 1. So the FSM needs to capture the sequence of ones. So we will need some sort of mechanism for this FSM to keep track of how many ones have been input to the circuit, or the sequence of ones that have been input to the circuit. And let's see how this FSM achieves that. So let us take the simple example of this 0 0 as being the start state. So when 1 is input, then this a new state is moved to, that is 0 1, another one is input, then a new state is moved to, and one more one is moved input, and then a new state is went to. So if there is a 1, if there is a continuous stream of 1s, so what is happening here is the output is always 0. However, this FSM is keeping track of this continuous sequence of 1s, and the moment and the first on the after a bunch of 1s, the first instance when a 0 is input, right, the output will be 1, and you observe that at no other point output will be equal to 1. So that is one thing, and also observe that at any state, say state 0 1 or 1 1 or 1 0, at any of these states, if the input is equal to 0, then the output is equal to a 1, right? And what that indicates is if there is a single 1 and then a 0, then after state 0 1, the output will be equal to 1. If there are two 1s and a 0, the output will be 1 here, right? So after 1 1, the output will be equal to 1, and if there are 3 1s or 3 or more 1s and then a 0, then this is the edge that sort of describes that that's the output. Also, at any state, so after this 0 has been detected, right? After the 1 to 0 transition has been detected, the circuit moves back to the initial state, that is state number 0 0, to again begin tracking the next sequence of 1s and the 1 to 0 transition, the next desired event. Once the circuit goes to the reset state, or let us say the start state, any number of zeros to the circuit here will keep the circuit in the same start state itself. So any number of zeros here will get ignored in some sense, or will not generate any output. However, a sequence of 1s, as soon as the sequence of 1 starts, the circuit keeps track of it by transitioning to the state 0 1 and then to state 1 1 and then 1 1 and then 1 0 and so on, right? So we will describe this circuit. Let us say, of course, in the class we've already seen that this is the implementation of the circuit. You've already seen this implementation, and you also have seen how to write the state table out of this. Let us say we didn't have either of them, and our job was, given the specification, right, given the plain specification saying that generate a circuit that detects a sequence, that detects a 0 after a sequence of 1s, we have zeroed in on this FSM, right? Once we have this FSM, it would be best to, one of the ways to get to the circuit would be to describe it in Verilog, describe the circuit in Verilog and feed it to the synthesis software, and the synthesis software itself will generate the gate level schematic or the gate level circuit for this FSM. So let's go ahead and describe the Verilog for this circuit, for the zero detector. So this is the module declaration, and Mealy zero detector is the name of the module. So we have to put how many inputs and outputs are there, and for that let's go to the FSM again, and the input and the output, how many inputs and outputs are there. So let's see this, how many inputs and outputs are there. So this is one input, right? This we will call this X, for example, and this is the output. This is one output, right? And possibly just call it Y. After that, we also know that this is going to be a sequential circuit, and there are 4 possible states. If there are 4 possible states, then we need 2 flip-flops, right? And each of these flip-flops will of course require the clock input, and let's assume we also have a reset input. That should be enough. So now we have inputs and outputs ready. So X, so let me write the output first, right? So Y is the output, X is an input, clock and reset are the inputs, and so that's in the module declaration. So X, clock, reset and Y. So the declaration is also sort of encapsulated inside the module definition itself. We are declaring the y out as reg because we will describe the behavior of y out. Y out, behavior will be described inside an always block, and it is going to form in the LHS in the statements inside the always block, and that's why y out is already declared as a reg here. So that is about the inputs and the outputs. We next have to describe the behavior of the states changing inside the as shown by the FSM, and also the behavior of the output y, as recorded by the FSM. So basically all the information that is there in the FSM will be written into the Verilog model, and let us go ahead and do that. So first of all, for saving current state and for for saving the next state variable, for example, we need a bunch of variables. So for which I'll go ahead and declare declare variables called, say, for example, current, state, and next state, right? And the state are actually, there are two bits for the state, so let me just write it 1:0. So that will do, yeah. So say present state and next state. What we basically plan to do in this Verilog module is write behavior in terms of say always blocks, right? Always at the desired event. If the present state is, if the system is in a certain state, then basically what we want to do is what will be the next state based on a certain function, right? So if for example, I could give an example. Let's say the present state is 0, 0, and what we want to now record is both the transitions starting from 0, 0. If the input is 0, then the next state will be equal to 0, 0. If the input is 1, then the next state will be equal to 0, 1. That is one set of statements, or that is one always block. So we need one always block to describe the behavior of state transitions, or let's say behavior of the next state, right? So when does our next states change, and what is the new values of the next states depending on what input, how the input changes. That is one always block. That's the first always block. The second always block that we want to write is basically describing the behavior of y. So for example, if the if the current state is 0, 0, and if the input is 0, then what is y equal to, right? We want to write that. And if the present state is 0, 0, and if the input is 1, then what is y equal to, and so on. We want to once we've recorded both of these activities from this FSM, right, the behavior of state transitions and the generation of the y output, we have completely described this FSM. All the information that is there in the FSM will now be present inside the Verilog module. So let's do that now. For programming use, right, we'll just save some bunch of constants called S0, S1, S2, and S3. And each of these basically are state assignments. So this is a binary assignment for the 4 states starting from 0, 0 up to say 1, 1. Yeah. Next we will define the behavior for output y and for the next state variables, as I've already shown in the with the FSM couple of slides before. Let's describe the output. Now this is described as the as the Mealy output, and the Mealy output by definition depends on both the present state of the system and the input. So we can use the same triggers. However, before writing the triggers, let's just understand what we want to write inside this always block. So the always block, all we have to do is in the present state, and that's the information given by the FSM, right? What the FSM says here, if the present state is 0, 0, and if the input is 0, then the output will be equal to 0. And if the present state is 0, 0, and the input is 1, then the output will be equal to 0. That is all with respect to outputs, with respect to the y output. That is all this FSM is giving. So we will do exactly that. So in the case, we will say check what state it is in right now, and let us say it is in state 0 0. Then all we have to do is if x, and we've written x in, right? So if x in, which means that if x in equals 1, then y output should be equal to 0. Else, right? Else if x in equals 0, write it clearly, right? Right, x in equals no, not of x in, that should do, that is x in equals 0. Then y out will also be equals to 0 actually. So I don't have to write both of these statements. I could just simply write if it is in state 0, then okay, let's just, if it is state 0, then irrespective of what the input is, it's x 0 or 1, just y out will always be equal to 0, right? Then for state 0 1, let me see what happens, right? So if input is 0, then output is equal to 1, and if input is 1, then output equals 0. And I can write that in the if this thing, but let's do a much shortcut, right? So if all I have to write is y out is basically equal to the complement of x in. That means when x in equals 0, then y out is 1, and x in equals 1, then y out equals 0. So that's done. And we'll continue for say 1 0 and 1 1 similarly, right? Now the events that we are interested, the trigger events that we are interested in is basically anytime state changes, right? Then this always block has to be triggered, and also anytime that x in changes as an input, then this block has to be triggered. So that will form the sensitivity list, state and x in. So yeah, state and x in is sensitivity list, and we are checking at what state it is. In the switch case block, we are checking what state it is in, and then depending on what state it is in and what input gets fed in, what is the output that is generated, and we'll see what the statements are. So yeah, as we already had written down, in state S0, irrespective of x in equal to 0 or if x in equal to 1, the output will always be equal to 0. And for S1, the output will be equal to the complement of x in, and the same behavior for S2 and S3 as well. So this is S1, and again S2, for example, if input is 0, then output equal to 1, and if input is 1, then output will be equal to 0. So that is sort of common in S3, S1, and also in S2, for example. Same thing. If input is 0, then output is, sorry, if input is 1, output is 0. If input is 0, then output equals 1, right? So this statement holds for all three states, S3, S2, and S1. So that describes the output behavior. So next we define the next state behavior, or the state change behavior. Again, the state change behavior, if the current state, the way we will write the statements is again using the case and end case statements. The current state behavior, when does it transition to a new state, is when the input changes. And so we are interested in again the current state, and based on what happens at the input, we will sort of record what transition should be done. So for example, S0, right? What I basically want to write is if x in, if the input equals is 1, then what will be the next state, right? So next state will be equal to S1, else, right, next state equals S0 itself, right? This is the kind of statements that we will write. So similarly for S1, what is the behavior? If x in, then if it's 1, then it becomes S3, right? So next state equals S3, and if it is not x in, that is if it's x in is 0, then the next state will be equal to say S0. That's the reset state that we're talking about. Similarly for S2 and for S3 also, we will capture the next state transition behavior. So And all of this, so this always block should get triggered when we should have this trigger when say a state change happens. Also again when an input changes, right, this has to be this block has to be triggered. So that's the set of statements we were talking about. At S0, if xn equals 1, then the next state equals S1, that is this one, and if otherwise the next state is equal to S0, that is stays in the same state. So we write the same four statements for all the four states, and that has completely defined the next state behavior. So we have now described the output and the next state. What we have now done is to calculate what the next state should be, given that the present state is one of these four and the input is as given, right? So the state change actually happens at the next positive edge. So that is the next thing that has to be sort of recorded, right? Assign the next state to present state, right? So this is the next state. So basically next state variable now is ready with the value that that should be the present state in the next clock cycle. So what we now have to do is to add the next pos edge, basically define a always block with pos edge as the trigger, and when the pos edge happens, what we have to do is the next state that we have newly evaluated should be sort of assigned to the present state, right? And that is what we will do here. At the pos edge of the clock, we are assigning the current state to be what was evaluated in the as the next state variable. This always block also has one more trigger, that is the reset trigger, and the reset trigger basically clears all of the two flip-flops, or all the flip-flops. So basically it just turns out to be the S0 state. So that's the output of both of the flip-flops are 0 0, so it sort of settles to the S0 state. So that is actually clear both flip-flops, right? So that is that's it. So we have included in this Verilog module all the information that is there in this FSM right now. So let's run through the code once to see how the code behaves, right? So this is the code. Let's say in your test bench you have just given a reset. So what happens when the reset is applied is of course at the negative edge of reset, that is when you make the reset equal to 0, this statement will get executed, the one that is boxed in here, right? So this statement will change the variable state, right? So the current state will be assigned to S0. So as soon as the current state S0 is assigned, state is now has a new value. So all those always blocks which have state in their trigger, in their sensitivity list, will get executed. So this is state is here and state is also here. So let us say both of them get triggered, and let's run the first always block, right? So state in right now the state is equal to S0. So S0, this line will get executed, and y0 will be equal to 0. So output equal to 0. So that happens in the as soon as reset is done. So after reset is done, state moves to S0 and the output will become equal to 0. Then the next always block will also get triggered. In the next always block, state is again S0 is the state. So this is the line that gets triggered. So now what happens, or the next state evaluation depends on x in. So let us assume or let us assign x in one after another, the two values, and then see what will happen. So let's say x in was equal to 0. So let's say x in equal to 1, because this is a circuit that detects the transition from say 1 to 0, right? So let's say x in was equal to 1 at this point. So if x in was equal to 1, then this is the if condition will get executed, that is if next state equals to S1. So next state will be assigned to S1. So S1 So next state will get now will be equal to 0 and 0 1, and at the next positive edge, right, where the next pos edge occurs, this this line which assigns present state, the next state to present state will execute. So now the new state will be equal to S1. So state will now will be equal to 0 1, that is S1, and now state has changed, right? So let me just clear this out. So again, state has changed. Now as soon as state changes, these two always blocks will again execute, and this time state equals S1, right? So this time state equals S1, and hence this case statement will execute, and y out will be equal to naught of x in, and in this current clock cycle input is equal to 0, right? In the previous clock cycle, when input was equal to 1, we had this next state change here, and in the current clock cycle, let's assume that the input is equal to 1, input is equal to 0. So if input is equal to 0, then y will be equal to 1. So basically we have just registered an event in which first bit was 1 and the next bit was 0, so y will be equal to 1, and so again this always block will also get executed, the second always block will also get executed, and in this clock cycle S1 will be here. This is the case that is true, and xin is equal to 0 now. So xin is, so that's the else statement getting executed. So the next state will be equal to S0, that is basically the reset state, and that's sort of setting up the system to start evaluating the next input sequence after this 1 0 event has been detected. So that is how the simulation will work. I encourage you to start with multiple with any input sequence and then see the execution sequence. So after the Verilog description and the simulation walkthrough, let us look at the sample test bench that's provided in the textbook. So this is the same test bench. Of course, we are drawing out the output from y out, and of course feeding the inputs x, clock and reset through the reg, and this is the instantiation of the DUT. That's done, and let's say we run the simulation for 200 clock cycles, and so this is the clock generation. 200 time units, and this is the clock generation. And the next is we'll basically run the inputs in parallel. That's what the fork and join block does. It creates a parallel process that runs these bunch of statements. So initially we will start off with the reset as 0, so or I think the correct way of writing that is just started with 0 and it goes to 1 and stays 1 for the rest of the simulation time, right, after 2 time units here. So then a sequence of ones and zeros for the x input have been given. So if I just write it in a horizontal manner, it will just look like this. However, we have to understand that the stable x input at the beginning of the clock cycle, beginning of the positive edge, is what is going to affect the state of the circuit, is what is going to affect what will be the next state values and so on. So before so just to understand that a little bit more, we'll just draw out the clock that will happen. So initially the clock is equal to 0, and for 5 time units the clock will be equal to 0. It becomes 1 after 5 time units and stays like that for 5 time units, and that sequence will get repeated forever until the simulation finishes. So in that, so the reset, this is the reset signal, this is the reset signal, and this is the clock signal, right? So this is at 5, right? Let me just write it fully. This is at 5 and this is at 15. So we now know where the positive edges are appearing, right? So the stable x value just before these positive edge, the stable x value here just before the positive edge is what count. And the way the fork and join block works is that each statement here is now running in parallel, right? So what is happening here is that x will be equal to 1 after 10 time units after the simulation has begun. X will be made to be equal to 0 after 30 time units after the simulation has begun, and so on. So basically each of these statements are executing in parallel, and that's because the behavior fork and join. Now so let's see, if you notice the test bench, it is making it's making a change in the x at the negative edge. So this is 5, of course. So 5 is 5, 15, 25, 35 are the time units when the positive edge occurs, and the negative edge occurs, of course, at 10, 20, 30 and so on. And you see that 10, 30, 40, 50 so on is when that's by convention that's when the x is changing. So let's try to map how x changes. So x becomes 1 at 10, and at 30 x will be equal to 0, and again at 40 x changes to 1, and so on. And then we will map the behavior, or we will observe the behavior at the rising edges here, right? So you can observe here that the rising edge, this is a stable value, and here it's a stable value, and so on. Except between this 50 and 52, so there is a small glitch, 50, 52 and 54. However, the positive edge arrives at 55, right? So here positive edge arrives at 55. So just before 55, the value is of x will be equal to 0. So that is what will be taken, and the rest of it is 70, 80, and we have a there was a minor error here. It was 90.